We heard about the talk on the Xenon by Elena Prile, that is undergoing searches, very fruitful and promising. We will hear about pilot detector by Sebastian Baum as a way, an alternative way to search for this type of models. Another scenario which could yield dark matter is within primordial black holes, and we heard yesterday the talk by Florian Kuhnel on assessing this possibility. But today, I want to talk with you about axions. So, this is a field that has grown in the last 10 years, and here I compare the attendance of Patras, which is the Axion workshop that's held annually. We see that the attendance has quadrupled, as well as the number of papers that have axions in the title in the Inspire in the last decade. So, what is the axion? Well, it's a byproduct of a solution proposed by Pechet and Quinn to solve the strong CP problem that lies within the strong sector of the standard model. And it all arises because of this Lagrangian, piece of Lagrangian that I wrote, in which this extra term, theta, along with a equivalent term that arises from like weak, yield to order 1 parameter, which would yield to effects that are not seen in nature. For example, a neutron would acquire a magnetic moment, which is not observed in nature, and this sets an upper limit. Perfect, thank you. Okay, so the neutron would have an electric dipole moment, which is not observed in nature, and sets upper limit on this quantity, which we expect to be of order 1. So one solution could be, for example, that this this quantity is a dynamical field, and then the Axion field would then be a new pseudoscalar boson, which whose energy density would be stored in the coherent oscillations of the field once it has acquired the mass. And when you study this problem in cosmology, you see that this energy density scales as the inverse volume, Hubble volume, which means that the energy scale of this scalar field looks like dark matter and makes up a good candidate for a dark matter component of our universe. So, how does all of this cosmology set into motion? Well, we have to postulate a new U1 symmetry with a new complex scalar field that's called the Pechet-Quinn field, which relaxes when the Pechet-Quinn symmetry breaks at the temperature of order F, which is a new scale that's inversely proportional to the axion mass. And at this moment, the radial mode of the Pechet-Quinn field sits at a radius that's of order F, while the axion field is the angular variable that sees the flat direction, and so it's a new pseudoscalar, and it's massless because of the flat direction. So where does the mass of the axion come from? Well, this comes from complicated, non-trivial QCD interaction with the QCD instantons, which tilt this Mexican hat potential and make the axion field oscillate about the true minimum of the theory. And it is these oscillations that make up the dark matter that we see today, possibly. This tilting, so all of this temperature-dependent effect is quite complicated to model, and there are nowadays numerical solutions with lattice simulations that are undergoing to pin down the QCD susceptibility, which gives the axion mass as a function of temperature, as we see here. Once we know what the equation of motion is for a scalar field with the Hubble friction in a cosine potential that's granted by the QCD instantons. Well, the axion field would start to oscillate when the Hubble friction can be neglected with respect to the axion mass, which is this approximation here. And we see that from this moment on, the boson starts to behave as dark matter instead of dark energy as it is for a higher temperature. So you have a transition from a dark energy-like equation of state to a dark matter-like equation of state. So I could just show you this picture and provide you with all of the information you need for the axion. I could speak about this for the 20 minutes that I have. This is the parameter space of axions and axion-like particles in general. We have on the y-axis the coupling of the axion to the photon as a function of the axion mass. For a given axion theory, so for a given Lagrangian, for example, KSVZ or the FSD axion models, you specify what's the interaction of the axion with the fermion that give rise to this anomalous diagram, which can then be computed and give rise to a proportionality between the coupling of the axion to the photon and the axion mass. This is why a theory for the axion lies on this yellow band. You have a proportionality constant. If you step away from this yellow line, you don't consider QCD axion anymore. You still consider viable dark matter candidate if you lie below this ALP, axion-like particle, called dark matter line. Anywhere here, you could have a viable dark matter candidate. And only on this line, you have QCD axions as they're built from KSVZ or the FSD models. Various experiments look for axions nowadays with the aim of probing the QCD axion line, as has done, for example, ADMX, which is the equivalent for axion for direct detection. Remember that this type of cavity experiment rely on the fact that the axion is the dark matter in order to acquire the required sensitivity, which is not, for example, the case for IAXO in the standard model. We see that there are various colors on this line. Well, so this is the line that tells you where the QCD axion would lie. But on top of that, if you also require that the axion is the dark matter, you have an additional requirement that pins down a narrow region here with an axion mass of the order of 10 to the minus 5 to 10 to the minus 4 electron volt. This is the region preferred by simulations for the axion mass, with the width of this window being giving the uncertainty in the production mechanisms, and the height giving the uncertainty in the model. If you assume that the axion is heavier, then you require a subdominant component, because otherwise you would overclose the universe. And you would overclose the universe if you step for lighter axions here. So what happens here? In order to avoid an overclosure of the universe in this region here, you have to fine-tune the initial solution, the initial condition of your axion field, so that the axion angle theta becomes much smaller than 1. So you have to pin down a specific value for the initial condition if you want to probe this inflation scenario. Well, this makes the physics of the axion dependent on the relative size of the scale f at which the Pacheco symmetry breaks, and the scale of inflation h. So this ratio is really a watershed between two completely different scenarios. The scenario in which the axion field is present during inflation, which is this region here, and the scenario in which the axion field does not participate or spectate inflation, and the Pacheco symmetry breaks after that. So to better see these models, let's start from the first scenario, in which the axion participates inflation. I've chosen to show the results by the Gambit collaboration from this year, which is basically a likelihood analysis over the parameter space of the axion. In this model, you see that in this scenario, the misalignment angle, which is the initial condition that you choose for your axion field, is directly related, is a one-to-one correspondence with the axion mass. I've done some work during the PhD on this, along with many other people on this scenario. And we see that if you want the axion to be the dark matter, your posterior probability peaks at an axion mass over 10 to the minus 5 electron volt, which, because of the bounds on the isocurvature fluctuation, would mean that you need a sensibly low amount of primordial gravitational waves. You need R to be smaller than 10 to the minus 13 for this type of axion mass. This is some model that, for example, Tommy Tenkanen in the audience is working on, and we are basically done with a model in which we embed axion in this type of inflation scenario. So stay tuned. The other scenario is a scenario in which axions, the Peccei-Quinn symmetry breaks after inflation, and this is quite more complicated from the numerics because we deal with the inhomogeneities and with the Kibble mechanism. So you basically have a string network that forms, as you see from this simulation, which is a 2D slice of a 3D simulation of the Peccei-Quinn field. So in this simulation, the colors code the value of the misalignment angle, so the axion field, from minus pi to pi. And you see that there are regions in which the axion field winds up around a dot, which is a line in the 3D space. And so this dot here represents an axionic strings. So you have a network of strings that evolves, interconnects, and radiates axions, so Goldstone bosons in the process. And this helps, it has to be taken into account when assessing the value of the cold dark matter today from in this mechanism. This has been done in a series of papers in the last 2 to 3 years. And they come to values of axions that are of the order of 20 to 100 microelectron volts. There are also compact objects in this scenario. So you have overdensities, which would enclose a fraction of your axion energy density within a Hubble volume. These are called axion miniclusters. And these overdensities here have been assessed numerically through the same simulation we've seen before. So this mini cluster would collapse at a temperature that's related to the matter radiation equality temperature, and they would have a density that's also associated to the density of the plasma at that time. If you look at these type of simulations, so if you integrate out as a function of the modes over the whole box, you see that with time evolving, the energy is injected at the mini cluster scale, so at the scale of the order of the Hubble size at that time, and also at a much smaller scale that corresponds to the oscillons that live inside the axion mini cluster. And this second feature here is not captured when you perform a WKB approximation. You really have to rely on numerical simulations on a grid for seeing this. So these are the first structure. The largest one are the axion mini clusters. They have a mass of the order of an asteroid, of a large asteroid, and the radius of the order of the Sun to Earth. Where the mass is related to the energy density of axion enclosed when the axion field starts to oscillate. The value of the mass is actually, of the mass of the minicluster is actually related to the value of the axion mass. So the 10 to the minus 10 scenario relies on an axion of 100 microelectron volt. This is what I've studied with Javier Redondo in a paper that we have yet to finish publishing, where we studied not just standard cosmologies, but also cosmologies that deviate from lambda CDM. And for the standard cosmology, we found the same value of the QCD axion mini cluster. One thing that I want just to mention is microlensing. So this is the line that you want to see. This is the line for the QCD axion, and this is the Subaru. So this is the same microlensing that I use to constrain primordial black holes. If you do that for axions and you perform a press sketcher formalism for these mini clusters that clump together, then you can say that for an axion of 100 microelectron volt in mass, you expect a fraction of mini cluster that's below 10%. So this could be a way to not to cripple, but to put some tension within the axion theory away from direct detection experiments. Say that your simulations that are now becoming more and more advanced are able to assess the value of f, the fraction mini cluster, and they find a value that's above 10%. This would be in tension with what you see from microlensing. So this would be something to explain. So this is something that will be performed in the next years in the field. So we also have much smaller and compact objects inside the mini cluster, we said. These are the Axion stars. This is work that I've done with people in the audience, Catherine Fries and Sebastian Baum, plus other people that joined our work. We have looked at what comes out of axions seen as a condensate in which all of the axions collapse to the same state. We basically were able to build a sort of a Hertzsprung-Russell diagram for the axion as a function of the density. So the inner parameter here that runs through these curves for different values of f is the density of the axion star at the core. And the different kinks tell us which physics is going on. So we just have gravity as the first step that keeps everything together, the quartic self-interaction, or the whole cosine potential for the axion. So now, I just talked about the QCD axion. I want to, in the last two slides, I want to focus on ultralight axions, axion-like particles, which have been mentioned during this conference here and there. Well, the axion stars on a much larger scale, which is the scale of the ultralight axions, can resemble, can describe what people see in numerical simulations with this type of particles. So if you want to simulate structure formation with ultralight axions, you have to solve for the Schrödinger equation in order to appreciate the wave-like nature of your Soliton core at the galactic size. So QCD axion forms axion stars, which are of the solar size. Ultralight axions, which are axions that are much lighter, form a solitonic core at the galactic size. Although they have different mass and different values of the F of the coupling. How do you get to this type of ultralight axions? One way is, for example, having actions from string theory. So you have, take a torus, for example. You have two different paths that are non-contractible, and they are distinguishable between each other because you cannot deform one into the other. You can show that for each of these paths, you have an axion-like particle associated with it. And now think of not of a torus, but of a 6D manifold, which is what people use for compactified string theory from 10 to 4 dimensions. Then this number of non-contractible manifolds, non-contractible path jumps to the order of the 100. And all of these would be axions with their peculiar mass that would form what's known as the axiverse. So what I've done with Sunny Vagnozzi, who's a graduate student that recently graduated and now is got his PhD last week, is assessing this axiverse. So we have here the value of the axion mass and as a function of the posterior probability. In the case in which you take the axion mass from string theory, so in the case you use the formulas that come out of string theory, and these peaks make the posterior probability peak at around 10 to the minus 22, 23 electron volt. Or if you relax this requirement and you just consider axion-like particle, then you have a much broader posterior probability distribution. What we have also depicted here are the different type of experiments that would be able to probe this type of scenario in the near future. This is a sort of timeline of the universe, because the axion mass is so that the axions start to oscillate when its mass is of the order of the Hubble rate. So an axion that has a mass of 10 to the minus 32 to 33 electron volt would start to oscillate now. So it would have behaved as dark energy until now. It would just now convert to dark matter. So anything that happens between here and 10 to the minus 27, which is the value of H at recombination, would be seen as a rotation in SIMB polarization. And whereas heavier axions, like ultralight axion, would show a cutoff in the matter power spectrum, similar to what we heard from Martina on neutrinos. Even heavier axions, including the QCD axion, can be probed through the black hole superradiance. And then in this mass range, we have the usual AMX, MEDMAX, and the whole number of experiments that are nowadays ready to take data. So these are my conclusions. Thanks.
Questions? Especially from young people. Yeah.
Thanks for a nice talk. Question about your last plot. So some of these masses on the left-hand side of the plot are very small. Does it really make any sense to talk about masses so small? Isn't the de Broglie wavelength of such an object much larger than the observable universe?
Well, that's the whole point. The fact that they have such a large de Broglie wavelength that they make up a condensate until they catch up with the size of the horizon.
Yeah. Question down here.
How much your constraints will change if you consider non-standard cosmologies other than lambda CDM? You briefly touched on that, but if you can comment a little bit.
you can have, for the QCD axion, okay, let's go back to the mother plot, the money plot. For the QCD axion, you can have the cold dark matter line, so this region here, could move anywhere in the allowed region between, this yellow band is bound below here by what I call Planck, which means that your axion decay constant F becomes trans-Planckian. So this sets a sort of natural limit. Here by observations of astrophysics and nature. In non-standard cosmology, so if you consider that at the QCD phase transition, your cosmology is not radiation-like, but something else, you can move this region here anywhere with the right value of the reheat temperature and the right equation of state. The downside is how can you build such a model? So it's very easy for WIMPs, because for WIMPs, if you have a TV modulus, you can build, you can change your cosmology at the electroweak scale. Here, this is 3 orders of magnitude below, and it's not that natural.